Today we're going to work through a simple 2x2 matrix example of doing the spectral method. Okay, I'll hand over the board down. Okay, so last time we defined an alternative to the method of norms. It's my term. Just to describe the first way we looked at convergence of Jacobi. And we showed the utility of the spectral radius S equals the maximum of the absolute value of the eigenvalues. And this is, for a small matrix at least, is relatively easy to compute, and we'll show how things converge. So what I want to do now is show you demonstrate now with a simple 2x2 matrix. So 2x2 example. So consider solving AX equals B, where A now is this matrix 3, 3, minus 1, minus 1. Now remember, we want to the eigenvalues that we're interested in are the eigenvalues of the B matrix. So first of all, we need to derive. We need to do things. So first of all, we need to derive B, which is D minus 1 L plus U for the Jacobi. And then evaluate the eigenvalues of minus B. Okay, and then to finally get S. So A is 3, 3, minus 1, minus 1. Now I've actually picked a matrix here which is symmetric. So and I can discuss more if you want to know more about the importance of symmetric matrices. It's beyond the scope of this module, but I can talk offline if anyone's interested. But actually by inspection, remember these L, we can just pick off the various matrices we're interested. L equals D equals U equals. Okay, so L is just the lower triangular bit and zeros everywhere else. D is just the diagonal, and U is just the upper triangular bit without any diagonals. Okay, so we're just partitioning off there. So, and then we use a result from before that B is D inverse times L plus U, which now we can just plug in. And actually what we're going to evaluate is minus B in this case. So we put the minus sign here, which equals, so D was just 3, 3. So the inverse of a diagonal matrix is just the reciprocal of its elements. Okay, so that's D inverse. And then L plus U is simply the sum of the lower triangular matrix, which has minus 1 down there, and upper triangular matrix and zeros on the diagonal. And of course we've got a minus sign in there. Right, we just expand that out. We get zeros on the diagonal, and we get a third, like that. So minus b is a third. Oh, no. You always know b has zeros on the diagonals. So the eigenvalues of this thing are just your standard calculations. So eigenvalues of minus b follow our standard rule. So we do minus b minus lambda I equals 0. So here, lambda here is the determinant of the matrix. So plug those in. So we just basically take lambda off the diagonal see if we can put this together. So we just then multiply the diagonal and take off the off diagonal. That implies that lambda squared minus a ninth equals 0, which implies that lambda equals plus or minus a third. Lambda equals plus or minus a third. We're interested in S, which is the maximum of the absolute values of lambda. So basically that's either of these quantities. It's the same. So absolute values of lambda gives a third twice. So the maximum value is a third. So what we can say there immediately is S is less than 1. Therefore this method Jacobi will converge for this matrix A. And if you have another method you want to compare, say Gauss-Seidel, then you can also compare with that. So this is a good example, and then basically see the tutorial for more examples of this. Okay. So for Gauss-Seidel, we know that B is D plus L inverse U, and if you fancy do it, you could evaluate B for the Gauss-Seidel case. It just gets you to have to do an inverse of a matrix, 2 by 2 matrix, which is something you know how to do. And then calculate the eigenvalues, and then S, which equals the maximum absolute value of the eigenvalues. Okay. S Gauss-Seidel should be less than S for Jacobi. Okay, and I'll leave that as an exercise for you to try in your own time. I try and occasionally leave a something for you to work out in your own time, so you sort of can engage with the material yourself. So that's one thing you can work out. There's more examples in the tutorial. Okay. Okay, so that's really finishing our sort of quite protracted discussion of methods for convergence. We've done the method of norms, which is diagonal dominance, and we've done the spectral radius method. The last thing I want to do, well, last but one thing I want to do on matrices, last thing is how we've so far we've been looking at AX. We considered AX equals B, the inversion problem, but there's lots of problems are eigenvalue problems. So we've used eigenvalues, but that's A VI equals lambda I VI. Now we've done the eigenvalue problem for small matrices, but how do we calculate lambda I when A is large? And you recall this forms the basis for this problem, forms the basis of our Google ranking algorithm, so-called page rank. So forms the basis of the Google page rank algorithm, which ranks websites in order of their popularity, or etc., or other criterion, and it's an eigenvalue problem. So the method for this, we'll just start today. Is called the power method. So if you had a 10, I mean, even you had a 1,000 by 1,000 matrix, and you went at that with your standard method of taking eigenvalues off the diagonal and trying to find a determinant, you'd be there forever. So there needs to be a more iterative method of solving this. And actually, if we look back at our Jacobi method, we were doing a big inversion problem, not by inverting the matrix directly, but by multiplying through by this related matrix B. So we actually, what we'd prefer to do easier matrix multiplication than an eigenvalue algorithm for small matrices. And actually this name, the power method, is because it involves here power method involves powers of matrix A. Okay, so that's where so this is actually a name of a method that involves how it's done. And remember, there's quite a few methods, Jacobi and Gauss-Seidel, which are just named after the people who've discovered it. It's not much use to us to remember how it works, but the power method has got how it works in the name. Okay. And I think it's timely to actually leave the power method to next time and shorten this video a little bit. Yeah, I just introduced it. Okay, so see you next time for the derivation of the power method.